Hello everyone. My presentation is about influences of biomass compositions, particle sizes, and the operating conditions of biomass fast pyrolysis. Biomass pyrolysis is a thermochemical process to convert biomass to bio-oil. There are several challenges at different scales in this process. At molecular scale, the molecular structures of different components in biomass directly influence the kinetics of biomass pyrolysis. At particle scale, the particle porosity, internal structures, shapes, and sizes influence the intraparticle, interparticle, and gas particle heat and mass transfers and fluidization operations. At reactor scale, the operating conditions of the reactor will influence the mixing and residence time distributions of biomass particles. All these multi-scale influences will lead to different yields and the quality of the products, such as bio-oil. To build the capability to simulate these complex multi-scale problems, firstly, we investigated a detailed biomass pyrolysis kinetics. In this kinetics, the biomass is characterized into cellulose, hemicellulose, lignins, extractives, metaplastic, moisture, and ash. And this goes to 32 chemical reactions, and the products are bio-oil, which includes 23 species, biogas, which includes 6 species, and biochar. The kinetics was validated with different experimental data. The first one is the pyrolysis of low-rolling pine. The second one is the pyrolysis of waste wood at a different temperature. So we compared the yields of biochar, bio-oil, biogas, and also analyzed the carbon, hydrogen, and the oxygen mass fractions in bio-oil and biochar, and also compared the light gas. The good match of products for different types of biomass provide evidence that this kinetics is valid for different types of biomass. Secondly, we proposed a hybrid drag model that captures the mixing of sands and biomass. In the pyrolysis of biomass with fluidized bed, there are usually different types of biomass and sands particles. For example, the sands particles, they are usually of high density and belongs to girdle B type. For the large biomass, they are usually non-spherical. Their fluidization characteristics are dominated by their shapes, and they also belong to girdle B type particle. There are also many small biomass particles, and these particles are usually of small size and low density, and they belong to girdle A type particles. And also during the pyrolysis, so even the large girdle B biomass particles will convert to girdle A particles during the pyrolysis reactions. So to validate and test different types of drag models, we designed a cold flow experiment, which we installed several high frequency pressure sensors and a high speed camera to measure the pressure drops, particle distributions, and then compare the experimental results with the safety simulations with different drag models. So after testing different types of drag models, we concluded that using a hybrid approach where the sham Auburn drag is used for the sands particles and the Ganser correction is used for large non-spherical biomass particles, and the filtered drag is used for the small-sized A type biomass particles, will provide the simulation results with the most accuracy in terms of pressure drops distributions, and the biomass distributions. Further extending the capability, we developed this MFX growth sphere simulation to resolve biomass shapes. So the biomass are irregular. The shape effects were only partially captured through drag models. This tool directly resolve irregular biomass shapes. So we firstly validated the capability using code flow experimenter, and then apply it to the simulation of a biomass pyrolysis with irregular shapes. So here, the gray particles are sands, and the enlarged video shows the biomass particles. To further extend the capability, we developed this 3D intraparticle heat transfer. So as said previously, the non-spherical biomass is represented with many grooved spheres. And for very large particles, we can't assume it's isothermal. So here we extend that different individual spheres will have a different temperature. For example, this sphere has a temperature, and this one has its own temperature, and they are uh, connected to each other, so there will be a conductive heat transfer between these two particles. And for particles on the surface, there's also a convective heat transfer with the gas phase, and also different individual particles will have a different pyrolysis rate due to the different temperature. So to build the glued sphere to represent the different shapes, we can simply using the cut cell method, which is originally developed for the safety simulation of different shapes. So we borrow it to represent, to generate the glued sphere. And then we use the surface cells tend to glued sphere for the collision, and then to then solve the intraparticle heat transfer on the glued sphere, which is also in the 3D grids. Then we validated the simulation with the spherical biomass and a cylinder biomass. So for the spherical and the very long cylinders, the 1D model using sphere layers is more efficient, but this 3D approach with glued sphere is more general to different shapes, and also can be directly coupled with the previously mentioned glued sphere reactor scale model. We also accelerated the simulation by using GPU computation. So we ported the DM solver to the GPU and then coupled it with the MFX safety solver. We tested the speed up in the simulation of particle packing and fluidized bed, and noticed a speed up of 120 to 178 speed up. And in the safety DM simulation of bubbling fluidized bed, we also observed a speed up of around 15. And for the DM part alone, the speed up is around 80. So we also reused the interface coupling and chemical reaction modules in MFX, so we can still simulate heat transfer and chemical reactions, as shown here in the simulation biomass drying. The temperature and the species profile compare well with CPU simulation. So we showed the capability to do this and to do that. And you may ask, in reality, what did you do? So from now on, I will give several examples. how we used the previously built capability to deliver some knowledge. The first case is the global sensitivity analysis investigating the influence of biomass compositions. So the first step, we using a Latin Hypercube sampling method generated many samples, each with different biomass compositions. Here we're using the detailed kinetics, if you remember. And then we import these biomass samples into the MFIX solver using MFIX Nodeworks to do the simulations and summarize the results. For example, the yields of biogas, bioil, and biochar. And then we build a surrogate model based on the simulation results. So the explicit equation form of the fitted surrogate model could be used for a quick estimation of yields without solving the stiff chemical reaction equations. The surrogate model is then used to do the global sensitivity analysis. So these three figures shows the sensitivity of biochar, biogas, and bioil to different biomass compositions. So the message here is that for oxygen-rich lignin and the carbon-rich lignin appears to have the most influence on the quantities of interest. So hence, any effort to reduce the uncertainty associated with these parameters or the reaction rate associated with these species could improve the accuracy of the modeling results. In the second case, we investigated size effects. So we simulated the pyrolysis of 3 different sized biomass particles. So this shows the biomass distribution, and the middle figure is the temperature distribution. And then we analyzed the residence time distribution, and we found that for larger particles, there's an increase of residence time, and the distribution profile also becomes broad. And this broad or wide distribution indicates small back mixing of the biomass particles in the reactor. And the temperature is uniformly distributed. So this is because for these small-sized particles, the gas-solid convective heat transfer is the dominating mechanism. The hydrodynamics also indicate a good mixing of sands and biomass. In other tested cases, the temperature are uniformly distributed around 740 to 760 Kelvin. When we look at the conversion, we see an increase of bioil and biogas. So this is because in the simulated bubbling fluidized bed pyrolysis reactor, the density of the biomass particles will decrease to 10% to 20% of its original value due to the thermal decomposition. These converted biomass particles are then evacuated from the top of the fluidized bed by the upflowing gas. The large-sized particles have a larger terminal velocity than small-sized particles. Thus, their residence time is larger and will be evacuated from the top when their density is reduced to a smaller value. The larger residence time of biomass leads to larger conversion and more yield of bioil. In the third case, we investigated the influence of different operating conditions by constructing operation diagrams of fluidized bed. So firstly, we simulated different particle sizes with different gas velocities in many cases. And then we checked the yields of bioil and also the residence time distribution of the biomass particles. So for the smallest flow rate, the bottom row, the biomass particles can be illustrated with a particle size equals or larger than 1.4 millimeter. The non-smooth distributions of the particles from 0.8 millimeter to 1.2 millimeter indicate the fluidized bed under these conditions were operated under plug flow conditions, which have larger fluctuations of both bioil and biochar in the outflow. These fluctuations will cause critical influences on the followed processes, such as gas-solid separation and hydrogen treatments due to the sudden change of loadings. For the highest flow rate, autofluidized bed with different tested biomass particles for operating smoothly. However, the short residence time may reduce the yields of bio oil. So uh, for a given particle size, the operator need to adjust the gas velocity to make a balance of a smooth operation over the fluidized bed and a good yield of bio oil. Conclusion. So a multi-scale biomass pyrolysis simulation framework is established. So there's a experimental validated hybrid drag model, experimental validated kinetics with detailed products, and the particle shape resolved DEM simulations, a Speedup simulation with GPU and coarse grain DEM, and also 3D intra-particle heat transfer. Then we use this to investigate the influence of different size, shapes, and operating conditions and inorganic compositions on the biomass fast pyrolysis. Thanks the support from NATO and Beto. This is a standard disclaimer.